Okay, so thank you for coming back. This is the final lecture of this module. There are too many things I want to say, so wish me good luck. All right, so this is a summary of the final point of last lecture on Monday. So remember, I have the wrong lecture notes on screen, most definitely. So I still didn't quite get it right. Sorry about that. No, I want the navigation panel, lecture 8, not lecture 4. Yeah, so you can see a bit of what happens behind the scene. All right. Okay. Now this is the lecture from this Monday last week. Okay, and the final point was on surreal numbers, we do have a derivation satisfying this property. So delta of omega is 1, the kernel is the reals, and the most difficult one, if you take a summable family of surreal numbers, then the derivative of the sum is the sum of the derivatives. Okay. Okay, and the way we've done this, so I summarized here the key points. If first you look at the logatomic elements, so the ones where you have a monomial, and when you take the logarithms, you keep getting monomials, so you can never split them into more pieces. And for those, we have the explicit formula. The justification is that this is the simplest function satisfying the right requirements to work in this setting. But you could use another one, actually, that there are other possibilities. Then you take for every surreal number, you take the set of parts, and the parts are, I remind you, the parts are these things that appear in this kind of picture. So you start from a surreal number like a monomial, then you go to the exponent, and the exponent is going to have maybe several monomials here. And the path is simply the sequence of monomials you find by repeating this procedure. You start with your number, you take a term, then you see another term here in the exponent, you go there. Now here omega is now logatomic, its own exponent is going to be log omega, etc. And the sequence of these terms is what is a path. And the derivative of x is going to be defined as the sum of a certain contribution for every path appearing in this picture. So everywhere you have of chasing monomials by going into the exponents repeatedly. Okay, so we have this definition, and the true reason why this definition actually works is that in surreal numbers there are no Christmas trees. Okay, so that's what Alessandro mentioned and left for me to prove, and I say prove quotation marks because there's no way I can actually prove it today, but I can give you some hints, somewhat repeating what Alessandro said in the Q&A, but not everybody is in the Q&A, so I'll make a summary for everybody. Okay, oops, what did I do? Great. All right, so the situation is this one. If you look at the surreal number, you can, as I said, look at the number, and then you draw this tree based on what the exponents do. So you take this one, this is e to omega plus e to log 2 omega plus e to etc., and you continue like this. If you start from here, the picture I'm going to draw is that at the root I put this monomial itself. Then I look at the exponent has 2 terms, so I'm going to draw 2 nodes here, and this one is representing omega, and this one is representing this e to log 2 omega plus, etc. Now here I have this node, its exponent has 2 terms again, so I have 2 nodes, 2 children, and I put log 2 omega here, and this other term here, and then what I have in mind is that there's going to be log 4 omega here, and another branch going in this direction, and this keeps going. Now, this is fine. So in serial numbers, you can build a serial number with this particular expansion, iterated expansion, you know, when you go in the exponents and keep expanding them as much as you can. What is not allowed is a configuration like this, where you keep bifurcating in all directions repeatedly. Okay, so for example, this one would be E2 omega plus E2 stuff, and there's a plus 2 log 2 omega at the end. And then the exponent here has the same shape, log 2 omega plus something else plus log 4 omega. So every time you see three terms, and the thing in the middle splits again into 3 terms. And now if I follow this path, the one going in the middle, this path, it keeps bifurcating both sides. And now this is not allowed in serial numbers. Why do we not want this? Well, because in this situation, if you look at the contributions of, let me draw them. If you look at the contributions of these green paths, so the path ending in this green terms, green nodes, these ones are going to be increasing, because every time you're going up here in this picture, actually you're moving left among these terms. So you're moving from something small to something a bit bigger, and you go into its exponent. And then you do this again. I mean, maybe you find yourself in log 4, but then the next path here is going to be a bit bigger, because the term here is bigger than log 4 omega. So the contribution of this sequence of paths will be increasing rather than decreasing, and that's not summable. Okay, so that's not going to work. Okay, and now how do we know that this doesn't happen in serial numbers? Well, I know one way of proving it, and it's this one. So you start from a serial number, write it in normal form, x equals to the sum of Ri e to gamma I. And now chopping these serial numbers, the serial number in particular means I either drop, wrong color, I either drop a tail of the number. It just means take the sum for, you know, up to some beta. Take this sum and I just truncate it. You know, I just drop some terms at the end. So I take some beta less than alpha and I take this sum. Actually, technical consideration, I take 0 less than beta. So I want something to still be there. That's a technical consideration. I mean, this is the key operation. Or another thing I can do, if I want, is, so when alpha is equal to beta plus 1, is a successor ordinal, so there is a last term, then I can do also something else. I can replace R beta with the sign of R beta, so with plus minus 1. And maybe, I can still chop, I mean, I can chop the exponent now. I can also chop gamma beta itself, the exponent of the last term. Technical consideration, as long as the last term remains the last one. This is technicality. I have to say it, otherwise I'm going to say something false. Okay, why am I calling this chopping? So you look at this tree here. Actually, let's look at the Christmas tree first. So I start with the term. Okay, with the term I can't do the first one because I'm already, the normal form is just a single monomial, so there's nothing to truncate here. But definitely this monomial is going to be the last one of this sum. It's just this one here. So I can go to the exponent and chop the exponent. For example, I could decide to do this. This will be a way of chopping this serial number. And in terms of this tree, that will mean I'm removing this branch here, I'm removing this guy. Okay. But then now I can start from this new serial number. I can do the same. I can go to this exponent. I can chop, I can remove the entire thing here. That will be a chop. And now the interesting chop I want to do is, I notice that now this is the last term of the exponent. So I can decide to go to its exponent and remove this one. That will be another chop. Okay, which corresponds to removing this, now this branch here. So chopping means, basically chopping means you can remove things to the right. Okay, so when I remove this one, it's fine because there's nothing else to the right here at this level, and there's nothing right of this one below this level as well. Okay, so I have to chop this one first and then this other one. Otherwise, I don't follow these rules. And now in this setting, and now you can see for this Christmas, I mean, anytime you have a Christmas tree, the thing you can do is you can do an infinite sequence of choppings. You can keep chopping this rightmost part. Every time you chop this one, you're allowed to chop the next one and keep going. Now, the theorem that we prove is that if X is a chop of Y, assuming this is a good use of English, but I'm not a native speaker, so I can do this. If this is a chop of Y, then X is simpler than Y. So the surreal number, so now you have to remember surreal numbers are these binary sequences of plus and minuses. The surreal number is getting shorter, it's losing pieces when you do this. And in particular, you can't chop infinitely many times. If you keep shortening your serial number, its length is an ordinal, so it's going to reach a minimum, and that's where you have to stop. So you have no choice, but you need to, you will reach a point where you can't chop your number anymore. Okay, now, so in this case, so a Christmas tree cannot be there because a Christmas tree is by construction something you can chop infinitely many times. So this definitely doesn't happen. Whereas this one is fine. If you try to chop this tree, you have to chop to the right, which means this is a single term. If I want to chop something, I have to go to its exponent, and the only thing I can chop is the entire second term. Or since the second term is also the last one, I can go to its exponent and remove the second term. Or I mean, this is still the last term, I can still go to its own exponent. But once I've done this expression becomes finite. Basically, the only thing I can chop is like removing this branch here and everything that happens afterwards. Once you do this, you see that you have only finite many things you can cut, you can chop. And so anyway, no matter how you start chopping this tree, after finite many steps, you're done. You can't do this anymore because of this. So this shows what's going on here. And in fact, the exercise that I leave to you is to show that X cannot be chopped if and only if X is a real number, or it could be a logarithmic number, but maybe with some coefficients, maybe plus or minus in front of it, and maybe you can even take the inverse of a logarithmic number. But that's it. These are the things that cannot be chopped. I mean, as soon as you have more, that as soon as the normal form contains more terms or the exponents are a bit more complicated than that, you can apply some of these operations and get down. But the thing is, however you start, whatever Surreal number you take, now however you try to chop it, eventually you reach this class here. Okay, so this is how we I can do this. Oh, Vincent is good. Yes. Oh, there's a mistake. Okay, so I made a small mistake. Actually, in the way I define chopping here, you can chop, every real number can be chopped to plus or minus 1. So the correct thing to say here is plus minus 1 union logarithmics plus minus 1 with coefficients and inverses. Thank you, Vincent. This is slightly wrong. So this setup on the screen is like this. Okay, so this is what we can do. We can have stuff like this, and this is enough to find the conclusion that we want. So in the case of this derivation, the key observation, the key thing to prove is that this thing is summable. And roughly what happens, it's not exactly what we do, but what I'm going to say probably works, but I would have to check. So that's why I'm saying oversimplification is that you take your family of contributions from the path of some x, okay? And now if this is not summable, then we can chop x to some y such that the family of the contributions of all the paths of y is not summable. Okay, so basically every time you have something not summable, here is the contribution of certain paths. You look at these paths and then you chase them, and you discover that by an argument in the style of Neumann's lemma with bad sequences, that actually if you have something not summable, then you can tweak your number x, actually remove some piece from x, and still have something non summable. And once you can do this, you keep repeating this, but you know that you can't chop things infinitely many times. So this thing cannot happen, which means that this is summable. So you actually get that this derivation exists. Okay. And then my note here is the converse. If there is Christmas tree, then there is x such that this is not summable. Okay, because we had this bad sequence of this path going up, getting bigger and bigger, that would give bigger and bigger contributions. Okay, so at the level of proving that these contributions are summable, this is essentially an if and only if with the condition that there are no Christmas trees. Whether there is a derivation is another matter. That's more delicate. Okay, and so this is about proving how you prove this. Maybe just one comment. How do we prove that if x is a chop of y, then x gets simpler? By being very careful. So you look at these two operations, and three operations actually that I'm describing here. One is dropping a tail of a Surreal number. The other one is replacing a real number with plus or minus. And the third one is chopping the last exponent of a Surreal number in normal form. And so we can verify that in these three situations, yes, the Surreal number becomes simpler. But you have to be careful. It needs to be exactly under these conditions. For example, this technical thing I was saying here, that the last monomial must remain the last. If it doesn't remain the last, then no, you don't get a simpler number, you get something else. You get some surreal number somewhere else along this tree made of plus and minuses. Okay, I'm definitely not going to tell you more about now how to do this, but it's a verification. But once you know what you want to get, you can get it from the definition of X that we've given in the first lectures. Okay, so we have this derivation. I'm leaving as an exercise. Actually, I'm going to fill these details in the uploaded version of the slides. But once you know, once you understand a bit this definition with contributions from the past, it's not hard to prove that, for example, the derivative of a number is 0 precisely when that number is real. Okay, which would be condition ST2 here. And just one of the two is trivial. So if I want to say, for example, if X is a real number, then the set of paths where X is just empty. And so the derivative of X is an empty sum. And that's 0. So one inclusion is trivial. One implication. The other one is a bit more tricky, but I'm going to leave this open for now, just not written here. And then just give you the solutions when after the lecture. Okay, now let's move to something that is now more closer to what Lau is doing in the other course about Hardy fields, which is, let's talk about the properties of now the derivation. And Alessandro Manda showed that the derivative is surjective. How? I use some general theory of H fields, almost of Hardy fields. So the ideas come from Rosenlicht. Look at this particular class here of, not quite of serial numbers, but of Archimedean classes of serial numbers. So you take positive infinite numbers, serial numbers greater than real numbers, and then you take their logarithmic derivatives, the x over x. And we're only interested in the Archimedean classes. Okay. Now take this class. This class has no infimum. There's no greatest lower bound for this class, because Alessandro was explaining that essentially this infimum would be the class of E2 minus a very long sum of these iterated logarithms of omega for alpha ranging over every ordinal number. That is not allowed because this is a proper class. So the normal form of this exponent is not of the right shape. It's too big. Okay, and then because of results of Rosenlicht on Hardy fields, but you can take them and apply straight away to H fields, like in this setting. This implies that this derivation is asymptotic integration. So for every f, there is a g whose derivative is asymptotic to f. So it's a good approximation of f. And if you couple this with an observation about how I know is a directed union of Hahn fields, this derivation is actually surjective. Okay, but we can say something a bit more. For example, we can say that delta is lambda free. Now, lambda free means that the sequence of the sums of derivative of log alpha times of omega divided by log alpha times of omega for alpha ranging over the ordinals, this has no pseudo limit in the serial numbers. And where is the analogy? The analogy is that, for example, psi has no infimum because this exponent here, this infinite sum, is actually as long as ordinals. And so this cannot be a Surreal number. When you look at this sum here, if you send alpha to infinity in the sense of ordinals, so if you try to take the pseudo limit of this one, you're supposed to get a sum over every ordinal of derivative log alpha omega over log alpha omega. And again, for the same reason, this is not allowed in Surreal numbers. So you know immediately that this is not going to have a pseudo limit. By definition, this implies that this says that this derivation is lambda free in the terminology of the book. Aschenbrenner, Van den Ries, and Van der Hoeven. Okay, and for the same, I mean, basically the same reason, it's also omega free, which is even stronger. And this, in this case, the sequence would be almost the same one, but with squares. This also has no pseudo limit. Okay, let me put a reference here. Go read the book. This is chapter 11. Okay, because the existence of this, I mean, in the same way, well, in a similar way as to the fact that psi has no infimum implies that you can find approximate solutions of the integral, the problem of finding the integral of f. The non-existence of this pseudo limit tells you something about other differential, well, finding elements satisfying certain differential inequalities. Okay, but I won't try to go there because that's, I will get it wrong anyway right now. In any case, the easy verification is this one. You can see immediately that these two sequences, they can't have a limit. Okay, now why now am I going into this? Well, I mean, I want to get closer to the fact that in transseries, in the sense of this field T, I mean, let me write this here, T with its own non-natural derivation, which in our case is just the restriction of the derivation of Surreal numbers, but this is also omega free and lambda free. Okay, so it's a property in common with the smaller field of transseries, the one you can build explicitly if you want from just a variable. Okay, but we can do more. We can say more. So let's start from, let me make first a general comment about H fields. This is more or less consequence of the work of Rosenlicht, but well, this one works for H field. If KD is an H field, then exactly one of the following happens. Okay, and following based on what this class psi does in the field K. So either psi K has no infimum. Okay, in this is the case. In this case, there is asymptotic integration. Or, like there's exactly two other things can happen. Psi K has an inf, but no minimum. So in this case, we say that there is a gap because then this inf is going to be sitting exactly between two special classes of Archimedean classes. So it's smaller than psi, but greater than all the derivatives of all infinitesimals. So it's going to be between the classes of the derivatives of all infinitesimals and this psi of k. this would be the gap. And then the last situation is if psi k is a minimum. And this is called what in the book is called grounded. So grounded H field is an H field where the psi has a minimum. In particular, if psi is a minimum, the H field is not going to have asymptotic integration. That would be case one. But this is also nice because it's like it is a bit better than the case where you have a gap. And now, why do we care about this? Well, there's a nice these grounded subfields, these grounded fields play a nice role in understanding transseries and Surreal numbers. So again, Aschenbrand and van der Hoeven, they prove that if this derivative in an H field is surjective and K, I'm sorry, there's also an extra condition that, again, I have to say, because otherwise what I say is wrong. The derivatives of the infinitesimal elements are infinitesimals. So this is condition of small derivation. This is a harmless condition. And now the last one, and K is a union of grounded subfields of the form let me say this a bit more precisely. Subfields that are spherically complete. And now if you're not familiar, just think Hahn fields, so Rm, for example. If you can do this, then Kd is elementarily equivalent to the field of transseries as a differential field. Okay, so this is a fun situation we have here. So we have a field, we take an H field where the derivative is surjective. So the H field itself is, in case one of this dichotomy, it has asymptotic integration. Actually, in this case, it has integration even. Psi is no inf. But then you want to write it as a union of subfields which are grounded, okay, in which this psi has a minimum. And now, if you have this, and the grounded subfields are spherically complete, so they're actually Hahn fields, for example, then that is enough to say that they satisfy the same first order theory as transseries. And maybe I want to make this comment here. So why is the derivative surjective on the entire field, but not on these grounded subfields? What's going on, for example, is that each grounded subfield has the property that this has a minimum. But if you remember what Alessandro was saying last time, what happens is that in any case, most elements of the subfield have an asymptotic integral in the field. There's only one monomial, actually one Archimedean, one class, one valuational class that doesn't have asymptotic integrals. And that's the one corresponding to this minimum. But then this class is going to have an integral in the larger field. Okay. And that integral is going to live in the larger grounded subfield. I mean, in another grounded subfield. So you're always, any element you take is always in something grounded, but you can always find integrals in if you go outside, and you get this. Now, in the case of Surreal numbers, now we can make this, we can verify this explicitly. So we can verify that Surreal numbers with this derivation, the simplest one, is also a model of the same theory. And the proof is by using this criterion here. Proof. I make this observation. Take a group of monomials in the serial numbers. Take one that is a set, not a proper class. Okay, so an actual group in the more traditional sense. Then, well, I can find a monomial of the form. I mean, I can take log alpha omega for alpha big enough such that this is so small that is smaller than any infinite element of M. Okay, and now I use this. Now, if I take the group generated by M and this element log alpha of omega, take its powers to make a group, this is grounded. It's grounded because this, if I take the derivative of this element, well, the logarithmic derivative of this element, so I do dx, oops, I went just a bit too far. Oh, actually, let me scroll down here. So when I compute psi here, and I do the x over x of this element here, this element here, that's going to be my minimum of psi. So this element doesn't have an integral in this particular field because it's the minimum, but this is grounded. It is spherically complete because in this case it's a Hahn field. And clearly now any serial number lives inside one Hahn field like this. Okay. Now there are adjustments I should make. So this is more of a sketch of a proof. Of course, I want this to be a differential subfield, for example, not just a subfield, but you can tweak the group M to make it closed. So some details to be added, very few, but I get the result. This is a model of the theory of transseries. Of course, as long as I put the right derivative here. Okay, because we know already that this derivative is surjective on serial numbers. So we have one ingredient from Monday, and now and this observation, this theorem here gives us the other piece. Okay.
Vincenzo,
and then, yes,
there is a chat of Elliot, and also
right. Yes, thank you, Elliot. Yes, there's yes, there is something I have not said. Yeah, sorry. So I stated the theorem wrong. So I'm going to correct. I'm going to own it and leave the mistake on the page. So you want this to be UV closed, which is a bit stronger than it's stronger than being surjective. So you can do integrals and logarithmic integrals.
And also
or exponential integrals.
But then also maybe there is something else. I mean, in principle, as it's stated, this could be the trivial union with just one field, you know.
Yeah, it could be, but then it wouldn't be surjective, because if you ground it, you don't have asymptotic integration. So you actually never have the trivial union. So the big field is in case one, and you write it as a union of fields of case three.
Yes, okay.
Yes. And in the case of serial numbers, UV closed, it follows from surjective because you have exponent log. So if you can solve, if you can do an integral, you can also integrate. You can take the log of a, okay, I'm going to say this wrong. But if you're surjective and you have exponent log, then you're also UV closed automatically, as Elliot is saying in the chart. Okay. And as Elliot was pointing out in the chart as well, the theorem here is how does it work? I can't say too much about this because of time and because it's not my place to do it. This implies that the differential field is omega free and Newtonian. Omega free is this condition up here. And Newtonian means that if you take a differential polynomial which is Newtonian, then you can find a solution which is in the, I don't think I'm not stating it quite right, but essentially you can find the root of the polynomial, of the differential polynomial. And there you really use this spherically complete to find solutions, because you want to apply the machinery that you want is not unlike what Alessandro was doing on Monday and saying that to find, if you have an asymptotic integral, you can find an actual integral by taking successive terms in which every time you integrate, you take the asymptotic integral of the error term. So you want to get better approximations of your integral. If you're spherically complete, you can just do it, and eventually you find an integral. Here you want to find approximate solutions of your polynomial, and you want to be able to go from those to an actual solution. But to do this, you have to do a lot of work, which I'm not able to do. Okay, and this says, in particular now, this says the surreal numbers have the same property. Certain differential polynomials have solutions here. So you have this Newtonianity, this kind of differential Enselianity restricted to this situation of H fields. Okay, so what happens afterwards? So we have a nice theory for the differential field, but there are more questions. I mean, there are two questions you can ask. One is whether surreal numbers with the derivation and exp satisfy the same theory of transseries derivation and exp, but I won't say anything about it. I don't know what's the situation here. I think Elliot is the person, is the expert in this. So I leave this to him. And no, I want to take this in another direction, which is, well, the transseries in T, you want to think of those as expansions, as asymptotic expansions of functions on the reals, for example. So germs of functions in some Hardy field. So this would be a sort of a quasi-analytic attempt, but with also with the exponential function. What is the corresponding thing here? Well, in the case of our omega, we had something corresponding to this. So let me scroll up on this side where I'm writing. Okay, now, so I can tell you definitely, if you take the surreal numbers in this R omega, these we can consider them as functions, not real functions, but surreal functions. Okay, because of course, I mean, these are proper class. So how do we do this? So let me give you a definition. The composition is a function. Well, let me say for now, let's stay in this context. You take something in the bracket of omega. You take a positive infinite surreal number, and you want to get a surreal number back. And what we want to do is, basically, I want to replace omega, which I want to think as my variable, with the positive infinite surreal number. Okay. It needs to be positive infinite because omega itself is positive infinite. So it wouldn't make sense to do something else, at least not in full generality. So what I want is, well, I want two properties. I want omega to be the identity. So if I compose omega with x, I want to get x back. And if I have an infinite sum composed with x, I want to get same infinite sum. And also, I want this composition to go up in the exponent. So E2 gamma composed with x should be E2 gamma composed with x. Okay. And first observation, if I just ask you these two things, clearly such a function is uniquely determined on this R omega, because this is generated by omega using log exp infinite sums. So with these two rules, this determines what it does. So if it exists, it is unique. Okay, let me give you a stupid example, right? I mean, I want to say if I take e omega square plus square root of omega, which are two elements of the R omega, and I compose this with x, I literally, I want to get this element back. I want this to happen. Now, theorem, we can do this. Okay, so this composition exists, and as a justification, you can see. And actually, I mean, you could actually go back to Schmeling, although you have to do a bit of to sort of translate certain things, and then you have to use this property of serial numbers with the Christmas trees. You need to use this. See also our paper in 2019. So we have extra properties. So it exists, but also we have, for example, that it's associative. If you do F composed with G composed with X, you can compose things F and G first, and then apply this to X. And this is increasing in the first argument. It's analytic in the sense that f of x plus epsilon is equal to f composed with x plus derivative of f composed with x plus derivative of f composed with x, derivative twice the derivative of f composed with x. I'm forgetting a small piece, right? Times epsilon square over 2, etc. So you get a Taylor series here for, well, at least when epsilon is sufficiently small. Sufficiently depends on f. So there's a sort of convergence radius for these expressions. And you even have that if x is less than y, then f composed with x is less than f composed with y. Okay, there's a star because the proof is in a footnote of our paper, because we thought we had a proof. There is also a claim in Schmeling, but actually both proofs are wrong. And then we realized there's an actual argument, but it's actually not written anywhere. I apologize. This is my fault. I mean, Vincent has been asking me to sort this out, and I haven't, not yet. Okay, so I have these properties here. A nice implication, for example, is that if I want to compute the derivative of f for some f in this R omega, well, I just do what? This is going to be the same as the limit epsilon going to 0 of f composed with omega plus epsilon minus f over epsilon. Because if you look at the Taylor series, you see that this has to be the derivative of f composed with omega, which is the same as the derivative of f by I forgot to say that the first line is actually two conditions. Omega is doesn't do anything on both sides. Oh yeah, which is a consequence of the first one anyway. But anyway, you can compute the derivative in this way. Okay, and as I suspected, I'm a bit running a bit out of time. I have one final comment to make. So this remark is just silence in 5. That's the thing I said. Lie in a convex class. So this was just a comment I had ready that there is really a convergence radius here of sort. So the convergence is, so this expression makes sense in a convex class. Anyway, but the radius is tricky to compute. Okay, now the final comment I want to make, of course, this is, we started with a nice theorem about the derivative on surreal numbers, but now I'm doing this composition on R omega. It's a lot smaller. Can we do this on all surreal numbers? Now, to make sense of it, I want to add this condition at least. So it must be some way of making sense of what the function, what this composition is doing outside of R omega. The answer here is no, for a silly reason that there is a very simple calculation, which is take L log omega of omega. Okay, and suppose that you can actually compose it with any logatomic lambda. Okay, so you can put anything on the left, not just things in R omega. You compute this, and when lambda is big, you write it down and you get an expression like this. So the numerator would be, comes from the formula for the derivative of logatomic when the logatomic is big. So see lecture 6. And this one comes from the chain rule plus the derivative of log omega omega. And the thing is, this is 1. It's always 1. And if this is always 1, then it means that this guy here, composed with lambda, has to be omega plus a real number. And that doesn't make sense. Okay, for example, because then there's going to be too many, I mean, this would be identity plus a constant, but it's clearly not what we want. So if you impose monotonicity condition 6, then you get a contradiction right away. There's way more logatomics than real numbers here. It just doesn't work. And the way to solve it is to, to really go beyond, the comment, and then I really should close the lecture, is to work with this. You have to solve that delta knows about exp log. So you want delta to understand log omega and its inverse exp omega, and the same for all the alphas, whatever those mean. And that's the thing. So you want to add, so you have to do 2 things. You want to find these functions. You want to give meaning to this log omega. We know what its derivative is supposed to be. It's supposed to be 1 over the product of all the finite logarithms of x. But we don't have the global function. But the thing is, we can build there is a simplest function, log omega, which satisfies these kind of properties. So it satisfies see, this is the Abel equation for exp. So log omega of x is log omega x plus 1. The Taylor series starts with the derivative of log omega. It's 1 over the product of the finite logarithms. It's increasing, and it grows slower than any finite iteration of log. There is a simple one like this, and that's the kind of thing you want to use. And really, the final comment, I promise. Oh, I haven't written it down. And the final comment is that now if you go look the latest preprints by Bakayoko, Van der Hoven, and Kaplan, and also just the first two authors, they do this, they do a lot of it. So the three of them build an abstract field of hyperseries where you have formal expressions containing X log, but also log alpha and X alpha for every ordinal alpha. And then Bagayoko van der Hoeven, you can see how you can now define the functions log alpha and X alpha on the surreal numbers in a way that gives you a large field of hyperseries. So they are making sense of this. I don't know exactly where it ends, because I think it's not finished yet. Certainly my lecture is finished now, so I'm going to stop here. I apologize, it's over time, but that's the end of the course. Thank you for listening all the way to the end.
Thank you, Vincenzo.
Thank you.
And thank you
very
Alessandro.
much. Thank you.
Yeah, thanks a lot.
So Vincenzo, what did you write at the very end? The exp omega of Thiers. What is Thiers?
Right, yes. So the analogy here is that, so the way I like to present this is that the logarithm is taking monomials from your Hahn field, or in the case of serial numbers, you have these monomials. You can't break them down. The monomials are something you can't break down as a sum of more elements. But if you do the log of a monomial, you find a purely infinite serial number, which is now a sum again. But then but for log, you find logatomics for exp and log. So there are things that exp and log are not able to break up into larger sums. Well, log omega is doing now the same thing for the logatomics. So the log omega of a logatomic is going to be something in this class TR. TR is a class containing actually the purely infinite numbers, but it's a bit bigger. And the exponential of a number in this class is exponential omega, or number in this class is precisely a logatomic, and vice versa. So you can parameterize now logatomics by truncated numbers, these numbers containing purely infinite. Yeah, so you can break out the logatomics, but then there's going to be log omega atomics anyway. So there's going to be things that log omega is not able to break into a sum, and that's why then you need log omega squared. So you need to go to the next iterate, and then you have to do this overall ordinals because serial numbers are so saturated.
Also a comment, when you compare the situation in the surreals with the results in the book, then you mentioned all this lambda free, omega free, but what is in the other context, the definition of log alpha is different, right? So in our
Yes.
case, we define the log alpha by certain logatomic numbers, in particular certain monomials, but in the book they define it differently, right?
Yes, so lambda free and omega free means that not exactly, you define a sequence of L alphas which behave like the sequence of log alpha omega in these real numbers.
Yeah, what I want to say
yeah.
is that they, in some sense, do a transfinite iteration of taking integrals, right? But they don't insist that these integrals are monomials or not. Doesn't even make sense.
Yeah, I mean, actually, the thing that happens here is that there are many sequences that can go here, and if one has no pseudo limit, then none of the others has a pseudo limit either. It's not this sequence could be, you can take slightly different sequences, and you will get the same condition.
Right.
Exactly, because there's no, in serial numbers we have these canonical choices, so we can choose log alpha omega is this lambda minus alpha, which is special. It's a monomial, it's logatomic, In a generic H field, you don't have monomials, but you can just take any sequence which fits into a certain pattern. And if that doesn't have a pseudo limit, then it's lambda free.
Right.
Yeah, and this is equivalent to a certain equation, no, to certain inequality having solutions.
But in our case, in the case of the surreals, in order to see that these sums do not have a pseudo limit, I mean, the easy thing to see it is because it's a sum of monomials, right?
Yes.
If
So
they were not, if they were not monomials, it would not be as easy to see that they don't have a pseudo limit, right?
Yeah. So the delicate thing is that there are, you can make up a sum over all ordinals, which actually has a meaning in serial numbers. So if I take the sum of, well, the trivial one, if I take a sum of 0 over all ordinals, I mean, the result is 0 anyway. But the thing is that in the case of serial numbers, these are monomials. So this is constructed the normal form of the limit, and you know that then the limit cannot be a serial number because the normal form would be as long as all the ordinals. So that's why we use that these are monomials, because this is actually a normal form. So you know the shape of the result. But if this is not a normal form, there may be cancellations along the way. So maybe your sum is actually trivial. Maybe the sum is actually 0 for stupid reasons. But these are monomials, and we use it to make this claim.
Yes.
I will stop the recording. Thank you again for both of you, Alessandro and Vincenzo, for the course.